Good morning, everyone. My name is Dr. Phiri Sibongile. My topic for today is a review of Tyred Gantry claims energy efficiency improvement based on energy monitoring, energy storage system, and optimal operation control strategies. My presentation outline is as follows: the background, the literature review, the model development, the case study description, the types of energy storage system, and the conclusion. The handling of containers and the motion of RTG cranes are powered by electric motors. For example, here in South Africa, the RTG cranes at the Durban container terminals operate daily, up to 24 hours, 362 days a year continuously. This means that a large amount of electrical energy is consumed. There are two main types of Tyred Gantry cranes, namely the standalone diesel-powered and the grid-connected one. The RT operation may be summarized into three essential movements. The first one will be the hoisting and lowering the spreader with or without the load. The second one is moving the trolley left and right with or without a load. And the third one is the gantry movement to move the entire RTG crane. The picture here shows the RTG crane motors. Most of the energy needed by RTG is in response to the demand from the electric motors such as the trolley motors, hoist motors, and the gantry motor. They are used for different movements described in the previous slides. Most of the researchers have done the review on the available literature published on the efficiency improvement of the RTG cranes, including the general operation and main components of the RTG crane, and also the energy monitoring of RTG cranes during their operation, and also the review on different energy storages has been done, as well as the different strategies and algorithms used for the optimal control and energy management of RTG cranes. The model development. The implementation of the optimal energy management model applied to the hybrid diesel generator and the battery RTG crane, aiming to reduce the operation cost, the amount of carbon dioxide emitted, as well as the peak power demand on the diesel generator, and also to maximize the potential energy recovered through the regenerative braking during the lowering mode. This is the diesel-powered RTG crane system with its different electrical components. The diesel generator connected to the DC bus through an AC or the DC rectifiers. The peak voltage may be reached when the host operates in the lowering mode. Since the motor acts as a generator here, therefore the regenerative energy will be produced. The second model is the hybrid grid or the battery RTG crane, to reduce the operation cost as well as the peak power demand on the grid. This is the grid-powered RTG with its main electrical components. The AC power which is supplied from the grid to the RTG clan system is converted to DC by an indirect rectifier seen in this sketch. The DC power is distributed through the DC bus to the gantry, the hoist, and the trolley electric motors. During the lowering of the load, the hoist motor operates as a generator, with the generated power passing to the DC link, which is recovered and stored in the battery bank, and this energy could be used to lift in the next load. The case study description. The analysis on RTG clan energy usage, as well as the approximate duration of Hentley cycle, having been analyzed by a few authors, showing that the load demand is highly nonlinear and is not influenced by the variation of seasons. Therefore, the measured power profile with the energy consumed considered as a positive, while the energy produced from the regenerative process is negative. Sketches here shows the daily measured energy profile, which is the used energy and the recovered energy. Due to an arranged nature of the container's weight to be handled in different cycles, the energy used as well as the energy recovered, and the length of this different cycle does differ significantly. And here in the picture, you can see that we have the energy consumed, which will be considered to be positive, while the energy produced from the regenerative process will be considered to be negative. Here is the 40-ton RTG clan power profile cycle at the full load. The peak demand during the hosting up phase is 292 kilowatt. The possibility of a peak regenerated power of 178 kilowatt during the lowering mode. Here the main phases are the hoisting up phase, the trolley moving left phase, the lower load phase, the hoisting up phase at no load, the trolley moving right at no load, and the lowering trolley at no load. Types of energy storage system. We have different types of energy system, such as the battery storage system. They are used to achieve both the peak shaving as well as shifting of the demand. And some of the benefits of energy storage system are power smoothing and the energy cost saving. We also have the supercapacitors. They could be used as storage for the RTG clan system. The supercapacitor could be charged while hosting down, and regenerative energy could be stored in the supercapacitors, rather than being wasted in the braking resistor. We also have the flywheel storage system to reduce the power demand from the diesel engine, increasing the engine life. Also to capture the regenerative energy and deliver it for the next container lift, and this could also reduce the fuel and the emission output of the system. The conclusion: the development of the two models was to minimize the operation cost and maximize the benefits of energy storage system. To review on monitoring RTG claims during the operation, such as improving energy efficiency. The studies focusing on power management system were limited to the use of optimization algorithms, such as the genetic algorithm, the FOC logic, and the game-based controllers. From the available studies, there is a lack of work combining the saving cost of grid-powered RTG gains with battery based on maximum demand charges. And also from the available studies, The optimal power flow of artificial retrofit with recovery was not studied. And thank you for your attention.